Would you excuse me a moment? I have a phone call to make, and I left my phone in here. It's a number that I've been calling quite a bit recently, so it's programmed into the phone. Find the phone under your seat there that's ringing. Okay? Would you like to press the orange button, please? It'll take the call, and then use it as an ordinary phone. Hold it up to your ear. Hello? Can you hear me on the phone?
Very clearly.
Good. Can you tell me your name, please?
Maxwell Charles Lovell Hall.
Hello, Maxwell. Have you ever used a cell phone before?
No.
Well, they're really rather fun things. What I'd like to do is to read you a couple of lines of poetry, a little bit at a time, and ask you to read it back to me. Okay? You understand? Here we go then. The mountain and the squirrel
The mountain and the squirrel
had a quarrel, and the former called the latter
The former called the latter
little prig.
little prig.
Thank you very much. I tell you why I asked you to do that, because there was once a very historic demonstration of one of the very earliest telephones that was made from this desk at the RI, and the words used by Professor Tyndall, who operated it that day, included that poem, and he had it read back from the other end of the telephone. And I thought it'd be rather nice to reenact that over the phone. Now, if you have another look at the control board on the phone, you'll see just below the orange dial, there's one marked end. Okay? So say goodbye first.
Bye-bye.
Bye-bye then. If you press the button now, that'll disconnect the call. Thank you for helping. And in case you're still not convinced that this is a really ordinary phone, I thought we'd call up one of the services. I chose Brain Teaser. Are you familiar with, do you use Brain Teaser? Well, if you don't, you might find it rather fun. I'll dial the number this time. It's 01, because it doesn't know I'm in London. 246 8050. Number's correct. So I dial it.
Which will both fit into the two blanks in the following sentence. A change in the number of votes in the blank constituency was truly blank.
Well, if you want to hear the rest of that problem, I suggest you call Brain Teaser yourself later in the day. The country is covered by a number of cells. At the centre of each cell, roughly a few kilometres across, there's a radio station and a computer. If you're on the move in an express train or in a car on the motorway, then as you cross over from one cell to another, the computer automatically redirects the call on a new frequency, and the whole thing happens in a 20th of a second. You don't even notice. So it combines the telephone with radio and a superb computer system. Just one other thing you ought to know, the computer also tells a second computer, which every quarter sends you the bill. The whole of telecommunications started, as so many other things, with an experiment done here at the Royal Institution by Michael Faraday. In 1831, he made the marvelous discovery that if you move a magnet in a coil of wire, you generate electricity. And that electricity led to another combination of a magnet and a coil will produce movement. It works like this. Here's a coil, and here's a magnet. Two wires go over here, and this indicator is another combination of magnet and coil. And when I move the magnet, the needle kicks. When I put it back, it kicks the other way. And I can pump that out. If I get the timing right, I can get a big swing going. Now, other people then developed that, so that this has been developed into a power station. And this has been developed into electric razors, washing machines, and railway trains. The whole of the power industry. Yet other people realized that those two wires could be very long, so that what you did here could send a message to the other end there. And the telegraph was invented only 6 years after that experiment. Morse invented his code, and we had the telegraph. The first undersea cable across the Atlantic went in 1854, when Queen Victoria exchanged telegrams with the President of the United States. But it was another 20 years before Alexander Graham Bell realized that if you made those two components small enough, then one could be attached to a diaphragm that vibrated in response to sound waves. And at the other end, a similar system would make the diaphragm vibrate and reproduce those sound waves. And we had the telephone. The idea of communicating without wires came along at roughly the same time. In 1865, the mathematician Maxwell worked out theoretically that light consisted of an interaction between a magnetic and an electric field. And he predicted other waves of the same kind that we now call radio waves. And it is said that he got his initial notions from a lecture given here by Michael Faraday. But again, nobody followed it up until 20 years later, when a young German called Hertz decided to investigate the properties of these radio waves and found he could send messages over short distances. This is a model of his transmitter that has been reconstructed by Mr. Bill Coates. We have an induction coil that passes sparks between these two brass balls, and attached to them are the large plates that act as aerials. Now, Bill, if you would like to transmit for me, please. Over here, we have a very early type of receiver with aerials out sideways like this. And in the middle, a detector that was actually invented 2 years later, we think in Paris, by a man called Branly, that's a little bit more sensitive than the very first. When Bill Coates switches on the transmitter, the sparks will come across there. The coherer will light the bulb. Let's try. And there we are. The bulb is lit, and it will stay lit until I tap the coherer, and out it goes. Let's try again. The bulb is lit, of course, by a battery. It's simply switched on by the receiver. Now, to send messages, you don't have to keep tapping that. At an early stage, that element was fixed to the vibrator of an electric bell circuit so that it was shaken all the time, and then you could pass bursts of sparks to send Morse code. That was then developed as a practical means of transmitting messages by Marconi, who managed to transmit messages up to 11 miles in 1898, and 3 years later managed to transmit across the Atlantic. Now, you may think that's a long time ago, 85 years ago. But remember that each of you has lived through an appreciable fraction of that period. In fact, my mother was old enough to be told about the transatlantic message in 1901, and now she can watch me giving this lecture on television. When broadcasting came along in the 1920s, the earliest receivers for picking up programs were called cat's whiskers or crystal sets. You have to have rather a long aerial. This goes up into the roof, and the currents induced by the radio waves flow through the set to Earth, and we should be able to get yes, that's working very nicely. But crystal sets, of course, are very faint because there's no energy. There are no batteries, no amplifiers. All the energy coming out of here is picked up by the aerial. So that you can join in and hear what I just heard, we've hooked it up to something a bit more modern, an amplifier here, and I'll turn it up.
Say dilly dilly, willy-nilly, dilly-dally. Ian, dilly dilly. The song.
Dilly dilly pom 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 pom.
That sounds like Radio 4 to me. The detecting element in that is a little crystal here with a wire that pokes onto it and exploits the electrical properties of a crystal. If we find the reception is not quite so good, I take the cat's whisker off and look for another point somewhere else on the crystal. That's a good one, straight off. Let's try again.
I'm glad you enjoyed that because we've just been faded off the air.
No, you haven't. That is being picked up live now. Well, we haven't time to follow all the history of telecommunications. So I'm going to concentrate on three rather splendid developments of the present day and see how good they can be. 25 years ago, the laser was invented and immediately offered the possibility of sending very large quantities of information along a laser beam. But you can't point it at a receiver because it might come onto rain and the beam gets deflected, or a bird might fly through it. So people decided to send it down a fibre of glass. Here's a piece of ordinary, quite good plate glass, and it looks very transparent until we try and look through it sideways and have not 1/4 of an inch, but say 4 inches. If we do that, it then looks very green because the glass absorbs quite a lot of light, actually. This one is transmitting only the green light. Now imagine that this block of glass, instead of being 4 inches, was several miles long. We would have to choose the optical properties of the glass very carefully and the colour of the light that we're sending so that we got the maximum signal out the far end. Here we have some rather thick glass fibres in black sheaths, and we'll show that light can be bounced along a thin filament and will come out the other end even if the fibres are bent. Let me offer that up to the lamp now. Can you see the light coming out the far end? If I put my thumb over the near end, they go out, and I could send messages in that sort of a way. The modern fibres that are now used can transmit very long distances. Down here is a laser, and its light is focused by a high-power lens at this point here into the end of a fibre that you might just be able to see glinting here. And that comes up through the shelf, takes a lot of turns around the drum, looped out here, and is then, the cut end faces a little screen over there by which the light comes out. Now, before the light goes into that cable, that fibre, we have a chopper disc that will interrupt it. I'll switch on the chopper motor and vary the speed. You should be able to see the light flashing on the screen, and it's actually sending a message in Morse code. Can anybody tell me what the message is? SOS. SOS, that's right. I think those are the three best known letters, 2 letters if you like, in the Morse code. Now, if we speed up the disk, gradually make it faster and faster, you couldn't read that as Morse, but the message is still coming through, and one could easily build a detector that would read it at that speed and write it out so that we could just turn it up to the maximum speed until it's just a flickering light. But those rates are quite trivial compared with the rates that a glass fibre can transmit. The bandwidth, the range of frequencies that a fibre can transmit is truly phenomenal, which is its other major advantage. TAT-8, the submarine cable, and telephone trunk cables now being installed around this country are designed to handle 565 million pulses of light per second. That is comfortably enough to describe all the information needed to print a complete copy of the Bible. At the British Telecom Research Laboratories recently, I saw a demonstration of 2,000 million bits or pulses per second going down an uninterrupted fibre that was 90 kilometres long. That's enough to send a Bible 4 times in 1 second. So gradually now, with increasing speed, this country is being rewired, not with telephone wires, but with glass fibres. That may sound like a huge operation. It means digging up all the roads and stripping the wires out of buildings. But in fact, it's easier than it might seem. It's easy to pull the wires out, of course, but how do you get the glass fibres in? Well, again, British Telecom have invented a very smart way of doing this, and they've arranged that we can demonstrate it here today. Here we have a plastic tube which can represent a telephone conduit. It comes from the loading machine here and comes along here, up the stairs. In fact, a number of you will find it close to your seats. Can you now hold it up so that we can see the entire length? It's a couple of 100 feet here. And you see there are coils at various points along it. It goes right up, along there, down and back here to the other end, which Mr. Bill Coates is holding. Now, I'm going to thread a system of 7 light fibres through that in a couple of minutes. And I'll show you how it's done. It's fed into the machine here from the drum, which rotates freely, and we blow it through with compressed air. Would you like to put the air on, Bill? We've also got a little green lamp at the end so that you can see where the end is. And some of you may see the lamp just down here now. And as the green lamp comes round to you, will you shout out here in a good loud voice so that we know exactly how far it's got? Okay? Here we go. It's beginning to go. Here. Here. Almost, almost. It's coming. I think there's a bit of a kink somewhere, you know. Does it actually stop, Bill? That, I think you'll agree, is a very smart way of threading light fibres down the tubes that will protect them and hold them within our buildings. When we get wired up, it's going to revolutionize the way in which we handle information. Not only will you be able to speak on the telephone down a light fibre, but you will have access to a tremendous amount of information. This is not the story of the future. It is for most of us, but a system that I'm now going to show you is already installed in parts of Westminster. It went live in October last, and customers are already using it. We have here what looks like an ordinary television set, but it is coupled up to a microcomputer, and it is interactive. We can ask it via a simple controller, very similar to the one you're used to, and the microcomputer will then arrange the program we want. Let's see from the menu what's on. Well, we have the usual television channels. Of course, we may not know what's on those, so let's go for A0 and quickly review the whole lot. There we have 16 television channels. You can see what's on all of them at once and decide which one we want to watch. Those are the 4 domestic channels and a number of special cable services and some European television channels that are all coming through at the same time. Not only can we watch television, however, we can have access to a video library disc. Let me call up library and see what films are available this afternoon. I think I would like to see British Garden Birds 1007. So I dial in 1007. Confirm, yes, that's the one I want, so I confirm it. And now it is going to look for the disc. A video disc is just like a compact disc, only it's got a film written on it, moving pictures. And this system is installed at Ipswich. I'm communicating with this handset with a system situated at Ipswich, where the video library is. It's now searching for the disc. And provided there is one of a whole row of video disc players available, they're rather like super-duper jukeboxes. And it's looking now for the video disc that I've asked for. It seems that there is a player available. It's just searching for the disc now, and it'll come up. There we are. BBC Video, British Garden Birds with David Attenborough. Now, I've got exclusive use of that disc. Nobody else can interfere with it while I want to watch it, until I switch off. Well, with all respect to David Attenborough, let's run on a bit, because we have complete use of this disc, so we can do what we like. We can go in slow motion. Isn't that beautiful? We can even stop it and go a frame at a time. What's more, we can say, well, I don't want to watch it all the way through. I remember there was a good bit somewhere. Let's look on the Facilities button. And it says to choose a bird. All right, let's choose a bird with button 8. No, I'm not particularly bothered with one of those. Hash for next list of species. So we go to the next page. Yes, I'd like to see the kingfisher. Kingfisher is number 7. So I press 7. And the laser beam that is reading the disc is now searching very quickly for the entry on kingfishers.
A call note and a country stream, and suddenly there's an
Let's go on and look for...
6.5 inches long with a 1.5 inch bill and an impressive turn of speed.
And he's caught the fish. Let's make him put the fish back. We run the video disc backwards now because we have complete control over it. And there he goes, flying backwards, tail first into the water, puts the fish back, and flies back to his perch. Lovely. If you come to the end of the film, there is a question and answer session. So it will ask you questions to see if you've understood. You can test your new knowledge by replying with the keypad, and it'll tell you whether you're right or wrong. We can also get into European television. If we go back now to the list here, if I call up B0, That is Italian television from Rome. That is the program that Italians are watching all over Italy at this very moment. And it's coming in to the fibre system that's controlling. It's more fun if you understand Italian, of course. The way in which that Italian television is received is via satellite. And satellites are going to be the next major topic I want to talk about. Very soon now, instead of getting it, or as well, if you like, as getting it through fibre to your house, you will be able to pick up satellites direct yourself. This is the sort of receiving dish that's necessary. It's the parabolic receiver that brings the radio waves from a satellite to a focus here, and with the correct type of receiving apparatus, you can then couple that up to your television. It won't be necessary to steer the dish to follow the satellite. As you all know, a satellite stays up because in its orbit around the Earth, the centrifugal force exactly equals gravity, so it stays in orbit. Now, it was pointed out 40 years ago by Arthur C. Clarke, the science fiction writer, that the closer to Earth you are, the faster you go. As you go further out into bigger orbits, then you travel rather more slowly, and it's further round. So at 6.5 Earth radii, 22,000 miles above the surface of the Earth, it goes round in exactly 24 hours. It's a bit like this, where these sticks show at their tips the position that it would be to scale on the model of the Earth. If that orbit is then arranged over the equator, it goes round with the Earth in 24 hours and appears to stay in exactly the same place. That's called a geostationary orbit. A satellite at that position can see nearly half the Earth's surface. And I suggest you might like to try this for yourself. If you've got a cheap little globe, you can make your own model. Or on any globe, cut a stick that is 5.5 radii and hold it over the equator, and then look with the system and see which countries can be seen. Because a satellite at that position can communicate with all the countries it can see, about 150 degrees around the globe. You could decide for yourselves then, as a mental exercise, where you think it would be a good place to put a geostationary satellite, bearing in mind what you know of geography, of the countries that can be seen, and the economics as to whether you think there will be enough traffic to make it worth the expense of putting a satellite that could see any two particular stations of that sort. There are a number of satellites of that kind up at the moment in use, and we have a model of one to 1/4 scale that is now flying in from the ceiling. This is an Intelsat, of which there are several in use. And you see the big wings out to the side are solar panels that collect light to give electric power to operate the whole system. On the main box itself, which contains the electronics, there are some little black painted jets which contain gas jets that direct the satellite and control its position. This is to make sure that it doesn't drift from the position we want. Once it's been launched, it has to be corrected from time to time, just a little bit, disturbed slightly by the moon, for instance. And it's also got to rotate on its axis, if you think about it, exactly once every 24 hours, so that it is always facing the Earth. And then out on this side are the parabolic dishes that receive signals up from Earth and transmit on different frequencies back down to Earth. And those are used for television and for data transmission, for computers, and for telephone calls. Over here, we've got a model of the Earth showing two satellites actually in position. Here it comes flying in. And as you will see, if you build your own little model, more that scale I recommend, but don't let me stop you being ambitious. The Indian Ocean satellite, which is over the equator close to the Seychelles, can just see Great Britain and Western Australia. They both see it rather low on the horizon, but it can act as a link between the two countries. So telephone traffic now to Australia goes first up to the British satellite station near Hereford, and then out to a geostationary satellite over the Seychelles, and then back down here to an Australian satellite station, which is a little west of Adelaide in Australia. There is one problem in doing it this way. Light and radio waves go at a very high speed, 186,000 miles per second. But it's 22,000 miles above the Earth, and therefore about 25,000 miles from Britain, and another 25,000 down to Australia. So it takes about a quarter of a second for the signal to go up there and come back down. If you're talking to somebody via satellite, you have to be a little bit careful about your telephone manners, otherwise you find you're interrupting each other. And for that reason, they make it a rule that on any telephone call, they never use more than one satellite, because otherwise it becomes a little too awkward to be convenient. However, all rules can be broken. And I said I would like to demonstrate this delay for you in this lecture. And British Telecom International said that they would be prepared to lay this on for the sake of the Royal Institution. So we're going to try something rather special. We're going to try to set up, here and now, the world's longest telephone call. Where do you think you would call to make the longest call? Sorry? Here, yes, exactly. If we call to Australia via this satellite, and then ask them to pass it on across the Pacific to Canada, and then across Canada to Montreal, and then we'll ask Montreal to send it over submarine cable back to London. And we have the two telephones here and one in the booth. And you hear exactly what's going on. So we're really going to put the telecommunication system to the test with a real live attempt at a demonstration. I have two trained assistants here, Anika and Alison. Would you like to come out? Now then, in order to demonstrate the delay, they're going to do a counting game. So we've just rehearsed that now. Would you like to start the counting now as fast as possible and good and loud?
1, 2, 3, 4, 5, 6, 7, 8.
That's fine. Fine. Thank you very much. Now then, Anika, if you'd like to take your end of the line here, and we'll put Alison over in the booth so that we don't get interference. We'll put her in a soundproof booth. And there's the other line there. And this is its number. And we're going to call this number round the world. Okay? When we actually get through, I want you to watch Alison's lips, because Anika will talk to her right round the world, and when she hears it, she will speak, and the message will come all the way back round the world until it gets down here. The total delay, if we get two satellites, as I hope, will be about getting on for 1.5 seconds. So if you watch Alison's lips, you'll see her speak, and then there'll be a pause before her voice comes back here, having gone all the way around the world back again. All right? Right, you know the magic number then, Anika?
Telecom International, can I help you?
Yes, this is the Royal Institution in London. Could you connect me to another London number via Australia and Canada, please?
Yes. What is the number, please?
01 409 1525.
Thank you. Just a moment, please.
Remember, it goes to Hereford, out over to the satellite, over the Seychelles, and the first connection is made here, and then by landline across to Sydney. Let's turn it round so that you can see.
Sydney.
Good morning, Sydney.
Yes, can I help you?
I have a call from the Royal Institution in London for a connection to Montreal. But Sydney, before you connect the number, would you please speak to the caller?
Yes, certainly.
Thank you. Go ahead, caller.
Hello, Australia.
Yes, Sydney, Australia. Can I help you?
Could you tell me what day it is and what the time is in Sydney at the moment, please?
Yes, it's 2:50 on Sunday morning.
Thank you very much. And what is the weather like?
Well, it's dark now, but it has been very, very pleasant.
Oh, thank you very much.
Hello, Sydney.
Yes.
The number is 1 for Montreal, 514 11801.
11801.
Yes, could you please extend the call to Canada?
Yes, certainly. One moment, please.
Thank you.
Go ahead, there's Montreal.
Thank you, Sydney.
Hello.
Good morning, Montreal.
Good afternoon.
And a call from the Royal Institution in London for connection to a London number. But before connecting the call, would you please speak to the caller?
I will.
Thank you, Montreal. Go ahead, caller.
You're welcome.
Hello, Canada. Could you tell me what day it is and what the time is in Montreal at the moment, please?
The time now is 10:50 a.m. and it's very sunny and about -10 Celsius.
Thank you very much.
Thank you, Montreal. Could you now extend the call to London? The number is
Yes.
01
Yes.
409 1525.
All right, just a moment, please.
Thank you, Montreal.
Got it.
Thank you, Montreal.
409-1525.
Thank you. Hello, London. I have a call for you from the Royal Institution in London. Go ahead, caller.
Hello, London. Could you tell me what the time is at the moment, please?
Just gone 10-4.
Thank you. And what is the weather like?
The weather's very cold.
Thank you. Shall we play the counting game now? You begin.
1,
2,
3,
4,
5,
6,
7,
8,
9.
10.
Thank you very much. Hello, this is David Pye here. Are the operators still hearing me?
Yes, we're here. I can hear you clearly.
I'd just like to say thank you very much for hooking this call up for us. The audience here greatly appreciated it. It
Thank
worked
you.
very
It's a
nicely.
pleasure.
Thank you all very much. Come out now, Alison. Thank you, ladies, for taking part. I think that was probably a world record to go round the world and back again on a single telephone conversation. I rather hope we can use this to get the Royal Institution into the Guinness Book of Records. And we have here Norris McWhirter, who has come along to witness it. Hello, Norris. Hello. Very glad you could come along and see what we're up to today.
Absolutely fascinating, and a world record by a very large margin.
Thank you. But if you think that the delay round the world via two satellites, I think we must have had there, breaking up the counting game with such long pauses, if you think that's impressive, as the man said, you ain't seen nothing yet. My third demonstration on telecommunications is going to be, I hope, man's longest ever telecommunication link. It's so long that it got 25,000 miles, the distance of a geostationary satellite, longer in the last 20 minutes. It all started on the 2nd of March 1972 at Cape Canaveral, when an Atlas Centaur rocket was launched carrying Pioneer 10 spacecraft. This is the actual launch of that spacecraft. It went out at a world record speed for that time of over 9 miles per second. It didn't go into orbit, it went straight out from the Earth as a single throw, and it reached moon orbit in 11 hours. You remember that Apollo took 3 days, but of course Apollo had to stop. This went straight on. The moon wasn't there at the time, the artist just threw it in to show that is the moon orbit. It very soon passed the orbit of Mars. It went out through the asteroid belts, heading for an appointment with Jupiter in the outer ring there. Because at Jupiter, it was deflected and gained a great deal of extra energy, which was enough to throw it straight out of the solar system. Its mission at that point, 12 years ago, was technically finished. As it passed Jupiter, Pioneer 10 took this picture on one of its scanners, showing the red spot, and the black dot is the shadow of the moon Io, the one with the volcanoes. And that was much the best picture that we'd got of Jupiter up to that point. There were, however, problems. First of all, could you shoot accurately enough to get exactly the right effect and come away from Jupiter at the right angle? Secondly, Jupiter has very strong radiation belts that could knock out the electronics and make the spacecraft useless. And thirdly, in order to get to Jupiter, you had to go through the asteroid belts, and many people thought that you'd encounter a number of bumps on the way and the spacecraft would be smashed up. Well, it did all three magnificently, and at that point, its mission was technically finished. But it was very well made. It's still working. 12 years later, it's still going out away from the Sun. It has already passed the orbit of Neptune and is now, at the moment, technically outside the solar system. Still going at 8.3 miles per second. Here we have a model of Pioneer 10. The spacecraft has an 8-foot dish, which is kept pointing at Earth and transmitting signals. On the short booms are the atomic power plants with atomic piles in there generating heat, fins staying cold, and a thermoelectric device making electricity from the combination of heat and cold. These are kept on booms to keep them away from the electronics. You can't use solar panels out there because the sunlight is much too weak. And on the big boom, out there are scientific instruments, a magnetometer for measuring magnetic fields, and also detectors for cosmic rays. That spacecraft, the real one, is now 3,500 million miles away from Earth. And it is still communicating with Earth and sending back data. Very shortly now, they suspect that the cosmic ray counts will take a dramatic change as the spacecraft moves out of the sphere of the influence of the Sun into what is really deep space. In September, my wife and I paid a visit to the Jet Propulsion Laboratory of NASA in Pasadena, outside Los Angeles. And they took us there into the control center of the Deep Space Net. It is just like the control centres you've seen on Apollo missions. Lots of computer consoles and screens and big wall screens and displays. And there they are controlling 16 different spacecraft that are well outside Earth orbit. They pick these signals up by 3 very large parabolic reflectors, one of which is in the Mojave Desert near Los Angeles, one is near Madrid in Spain, and one is down near Canberra in Australia. And those are cleverly positioned so that they are about 120 degrees apart, so that as the globe rotates, one of them can always be seen from any angle, so that they never lose contact when they want to with any spacecraft. As you turn, wherever you're sitting in the hall, you can see one of those antennas all the time. They are sending their information into a controlling network center in Maryland, from which it goes over to Jet Propulsion Laboratory and then is distributed to the various laboratories that are handling the information and analyzing what's going on. Well, Pioneer 10 is much the furthest. It is therefore the longest link. So we asked NASA, is it possible you could switch Pioneer 10 on for the lecture at the RI? And they said they would do their very best. So I hope that a little over 10 hours ago, they sent a signal up to tell Pioneer 10 to switch on. The signal took 5 hours to get there. Remember 1.5 seconds around the Earth and back? It takes 5 hours to Pioneer 10. If Pioneer 10 responded, it started sending data back 5 hours ago, which are now being received in Canberra. It was switched on from the United States, but in 10 hours, not only do the men working on the shift clock off until we have a new team, but the Earth rotates by 150 degrees so that the United States can no longer see it, and it has to go into Canberra and be routed via satellite over the Pacific to Maryland, to Jet Propulsion Laboratory, and then north to Pioneer 10 Laboratory outside San Francisco. There is somebody who is going to arrange all this for us, called Jack Dyer. And here we have the RI NASA hotline. I'm going to call Jack Dyer now and see what news he has for us. Hello?
Hello.
Hello, is that Jack Dyer?
Yes, it is.
Hi, this is David Pye. We have a very enthusiastic audience here. And I've just been telling them a little bit about Pioneer 10. Are you in contact with Pioneer 10 at the moment?
We are. We're getting the data here in the control center near San Francisco. Shall I put it on?
Well, just tell us a little bit about how you're receiving it first. I said it took 5 hours to Canberra.
5 hours and 2 minutes old when it reaches the Earth, and it arrives at our tracking station near Canberra, Australia, and is relayed here via satellite. And it'll take about a quarter of a second to get from here to you via another satellite 35,000 kilometers out. And as I say, even so, it's 5 hours and 2 minutes old.
That's splendid. Could we hear the train, please?
All right, I'll put it on now.
That's it. That is a carrier wave being broken up every few seconds into a train of pulses that are being received now in Australia all the way from Pioneer 10. That was,
Hear that all right?
that was absolutely splendid. Thank you very much for laying it on for us.
You're welcome. Thank you for listening to our spacecraft.
Well, we quite understand what a lot of trouble you've had to go to get this signal live into our lecture, and we all very much appreciate it. Thank you very much indeed, Jack. The spacecraft has enough power and fuel for adjusting its position on board to last for many, many years, perhaps 40 years. So we may be listening to Pioneer 10 and getting exciting information from way outside the solar system for a long time to come. Well, the dishes they use, as we saw on the globe earlier, are 64 meters in diameter. That's 210 feet, and the total collecting area is equivalent to 12 tennis courts. Nevertheless, the amount of energy that's actually received is very minute indeed. The total amount of energy falling on the Earth is very small because an 9-foot dish produces a beam of 2.5 degrees, and it's a long way out, and 2.5 degrees gets very big. Just to show you how big, we have a slide showing the orbits of the inner planets. The third one, of course, is Earth. The Sun and the Earth there are drawn much too big, but the orbits are to scale. And this has been arranged to produce a patch of light equivalent to the beam of Pioneer 10. And it's that big. You see, it easily contains the orbit of Venus. It's nearly as big as the orbit of Earth. So as the Earth goes round in a year, they have to slightly adjust the position of Pioneer 10 so that they can follow it all the time. In a few years' time, it'll be even further away, and the Earth will go round for a whole year, staying within the beam. Now, that beam is transmitted at a power of only 8 watts. There's only 100 watts produced by these power plants. 8 watts is about the amount of light that was coming out of that torch. But you see how much it spread. The whole Earth intercepts only about a 50th of a millionth of a watt. At the focus of the Deep Space Net dish that's looking at it, the energy is 10 to the minus 18 watts, a millionth of a millionth of a millionth of a watt. NASA gave us a nice analogy here. They said that if they were to collect that energy for 100 million years and store it, at the end of that time, they would be able to light one small Christmas tree lamp for 1,000th of a second. And that's the signal you were listening to live over the telephone a few minutes ago. I think it would interest you to know in which direction Pioneer 10 has gone. If you go out on a clear evening at this time of year and look in the southeast, you'll be able to pick out Orion and the 3 prominent stars in a line of Orion's belt. I'm sure you know those 3 stars already. And up above those, the very bright star Aldebaran in Taurus. Just about halfway between those, and just a little to the right, where we've put the yellow dot there, that's the direction in which Pioneer 10 is going. There's another space spectacular coming up in just a couple of weeks. On the 24th of January, Voyager 2, which was launched long after Pioneer 10, will be coming up to Uranus. It passed Jupiter in 1979, maybe you remember. It passed Saturn in 1981, but it's got different problems out at Uranus. First of all, it's a lot further away to send real pictures. And secondly, it went through the moon systems of the first 2 planets in the plane of which the moons are orbiting. So it could turn and look at each in turn. But Uranus is tilted on its side. So as it comes in, it's like going into a dartboard. You see a bright star, that's the sun, and it twinkles as it goes round behind the rings of Uranus. And now it's cut off by Uranus. This is an impression of the actual trajectory after the pictures have been taken. And the sun will come out again. You see how small the sun is at that distance. This is about half the distance of Pioneer 10. And now it'll be occulted by the rings again, twinkling as it goes there. And in another 3.5 years, Voyager 2 will go on to meet Neptune, at present the furthest planet out from the Sun. They were unable to give us data from Neptune, from Uranus at this point, because it will have to take its pictures in a very short time. The time of flight of the signal is 3 hours at the moment to Uranus. But the close-up pictures, all the best close-ups that you will see in a couple of weeks' time on television, will have to be taken in a period of about 8.5 minutes, because it's flying through the plane at right angles, and it'll have to turn very, very quickly and take all its close-ups before the distance starts increasing again. So the computers on the ground and on board the spacecraft will have to know exactly what to do well in advance, and they're busy working on this to make sure it's exactly right, because if it goes wrong, it'll be much too late to get in touch and say, just one more, please. It'll then be way beyond by the time we get a signal out to the spacecraft. If we go back to Pioneer 10, Pioneer 10 is still going. It's been going uphill from Jupiter for the last 12 years, and it's slowed down a bit, only 8 miles a second now. But that is a speed that the Sun can never pull it back. The Sun's gravity is getting weaker by the inverse square law at that distance, and it will never fall back. It will keep on going, and in 32,500 years, it's going to come close to another star, a rather nearby star, only 10 light years away. It's just possible there might be somebody around there to see it and take a look at it. And so before launching it, they put a plaque somewhere on Pioneer 10 that would give them some information about who sent it. And there's a representation of the plaque that is carried by the spacecraft. It shows here a line diagram of the spacecraft itself. That should be a good hint to anybody. And in front of that, what we look like. They may wonder why there's two sorts of us, but then there are good biological reasons for thinking that even aliens come in two sorts, because there are good genetic reasons for it. Down the bottom here is a diagram of our Sun and all the planets, showing that the spacecraft came from planet 3. And this diagram shows the position of our Sun in relation to a number of pulsars. Those are stars that flash at very high rates, and the rates at which each one flashes are written in digital code in relation to the time of relaxation of a hydrogen atom shown up here in its two states. So if people are clever enough out there to catch Pioneer 10 and take a look at it, they should be able to interpret, if they put their thinking caps on, what those rates are. And by looking up in their star atlases, they're able to find out which star originated this system and where we are. Such is the pace of technology that within your lifetimes you may see the first communication between people and aliens on another planet. You might like to wonder how we will start to establish realistic communication with people who may share none of our normal attitudes or experiences. They may have a very different way of life altogether. And how do you strike up a conversation, as it were? There will, of course, be an enormous lag unless we find some way of signalling faster than by light and radio. That's quite a thought to finish on. In the next lecture, we'll be looking at the most complicated and sophisticated communication system that has ever been known on this Earth, and it exists within our own bodies. Thank you very much.